And this question says, discuss the shape of following molecules using VSEPR model. 5 molecules हैं और हमें उनके shapes discuss करने हैं VSEPR theory के हिसाब से. और क्या क्या है हमारे पास जिंदगी में? Well, हमारे पास है BeCl2, BCl3, SiCl4, ASF5, H2S और phosphine. So let us first take a look at the first member, BeCl2. BeCl2, if you start analyzing the central atom is beryllium and it is linked to 2 Cl atoms, each enjoying 3 lone pairs, which is fine. Now, if you look at the number of electron pairs around the central atom, because in VSEPR theory, what matters is number of electron pairs around the central atom. How many electron pairs do we have? Well, we have 1 and 1, 2. So steric number as we call. What is steric number? This is number of sigma bonds plus number of lone pair of electrons. Now, on central atom. This is on central atom. Now, how many sigma bonds are formed by beryllium? 1 plus 1, 2. And how many lone pairs are present on beryllium? 0. So, steric number is 2 plus 0, which is 2. And when the steric number is 2, that means we just need 2 orbitals on beryllium. And well, how would be those orbitals? They must be opposite to each other. If they are just opposite to each other, what happens? You have Be. Now, if Cl atoms repel each other, as per VSEPR theory, they want to go as far apart from each other as possible. And the most apart they can go is they are just opposite. If they are just opposite, this bond angle is 180 degrees. And the structure is linear. Wow, is it linear? Yes, very much. It is linear. This brings us to BCl3, the second in the line. If you try to draw BCl3, well, and you can also try to find out and figure out the steric number of boron in BCl3. Boron is surrounded by 3 Cl atoms. It is connected to 3 Cl atoms by 1 sigma bond each. So, steric number. What is steric number? You might say that I don't know what is steric number, so I am telling you very simply. For central atom, the number of sigma bonds plus number of lone pairs. I have just drawn Lewis dot structure. You can see number of sigma bonds is 1, 2, 3. So this is 3 and number of lone pairs is 0. So this is 3. And if the steric number is 3, with each steric number is associated a certain geometry, a certain configuration around the central atom. Like in this case, we will have trigonal planar. So the geometry would be trigonal planar because Cl atoms would like to go as far apart from each other as possible, and the farthest they can go apart from each other is at an angle of 120 degrees within the same plane. So this becomes trigonal planar as per VSEPR theory. Very quickly, let's take a look at the remaining ones also systematically. The next one is SiCl4. If I draw the Lewis dot structure of SiCl4, I'll draw it all very systematically before you. Steric number will be equal to 1, 2, 3, 4. 4 sigma bonds plus 0, which is 4. And we have learned the table, we understand and we remember that the geometry associated with this would be tetrahedral. How exactly does it look like? I'll actually show you these animated molecules also. Wow, is it? I mean, first of all, very simple, so we can skip them. But right from 3-dimensional tetrahedral molecules, we will take a look surely. And what about the next one? ASF5. ASF5. If you just consider, the geometry is very interesting. It is trigonal bipyramidal. And why is it trigonal bipyramidal? Why so? Because if you observe the steric number will be 5 plus 0, which is 5. Oh wow, that is the case. Yes, that is the case. Then we have the lovely H2S and phosphine. Till now, please note the number of lone pairs on central atom is 0. And when you talk about H2S and phosphine, the story slightly changes, because in H2S, you have H, S, H, and in phosphine, you have P, H, H, H. If you watch the steric number, it is 2 plus 2, which is 4, and it is 3 plus 1, which is 4 again. Oh my God, that means the geometry should have been based on a structure which is very similar to tetrahedral. Maybe, whatever. But for sure, one thing is there, it is definitely not linear. And you find that lone pairs also occupy certain space, and they repel and they push around, and thereby, because of all that push, the structure becomes angular. Oh my God, this is angular. Yeah, sometimes people call it angular, sometimes people call it V-shaped. You can call it whatever you like, both are good words. What about phosphine? Phosphine also is very interesting. See, you have 3 bonded pairs and 1 lone pair. If you observe, these are roughly at the corners of a tetrahedron, but since lone pair cannot be seen, so all you can see is phosphorus with H, H, H. This is all what is actually observable or is visible. And in that case, the geometry is termed as, yes, it is termed as trigonal pyramidal. It is trigonal pyramidal. Right? Right. Watch out for this very lovely tetrahedral structure of SiCl4. Can you observe the very unique tetrahedral geometry? Can you observe that all the 4 green colored atoms, the Cl atoms, are at same distance from the central atom of silicon? SiCl4, tetrahedral, is a perfectly symmetric structure. Observe this tetrahedral structure very carefully. I mean, the way we have put it here, see, if you join all the corners, this is the tetrahedral structure, and actually you would find that it consists of 4 equilateral triangles. How exactly? It is simple. An equilateral triangle, and from the centroid you take a perpendicular at a 4th point there, and this is the shape of a 3-dimensional tetrahedron. 1 face, 2 face, 3rd face, and the bottom 4th face. This is a tetrahedral structure. Now observe the trigonal bipyramidal structure of PCl5, yeah, ASF5. If you notice, there is a central atom, and to this central atom are attached 5 different fluorine atoms. And I have a few things more to add. Why do you call it trigonal bipyramidal? Because you have central atom, arsenic, then you have F and F and F, like this. And these 3 locations are called equatorial positions. Fine. And what else? And you have 2 more F atoms, and these are called axial. Why exactly? Please note that the angle between equatorial and axial is 90 degrees. So axial equatorial is 90 degrees. On the other hand, if you notice this angle between different equatorial angles, this is 120 degrees. Equatorial is 120. So is this a very symmetric molecule? No, it is not as perfectly symmetric as tetrahedral. Why? Tetrahedral had all bond angles perfectly equal, everything identical. In this case, my dear, there are 2 different locations. Axial bonds are longer and weaker. This is additional information I am giving you. Axial bonds are longer and weaker, while equatorial bonds are slightly shorter and stronger. That is the speciality of this trigonal bipyramidal geometry. You can see that these two can you see that this angle is around 120 degrees? So this is equatorial. And this, they are perpendicular. This is axial. And there is one more small equatorial at the back. This is the structure of ASF5. Observe the most unique trigonal bipyramidal structure once again in its three-dimensional movement. This brings us to H2S, dears. H2S, the simple angular molecule. HSH, and as you can see, this is not a linear molecule. Why? Because there are lone pairs of atoms lone pairs of electrons, sitting on sulfur atom, which actually repel and make this molecule non-linear or bent. And lastly, we come to phosphine, PH3, a beautiful trigonal pyramidal molecule, phosphine. This is a lone pair sitting at the top of this location, you can see, which actually pushes the hydrogen down and gives you this trigonal pyramidal structure.